morning, children. We are starting chapter 12, Discrete Mathematics. What do you mean by this word, discrete mathematics? It was actually developed in 19th and 20th or latter centuries. It involves distinct values which are either finite or countably infinite. Like natural numbers, I can give an example where I can create a one-to-one mapping from the given non-empty set to natural numbers. Like whenever I am able to say the next elements, we say countably infinite. Branches of discrete mathematics, some of them are combinatorics, mathematical logic, Boolean algebra, graph theory, coding theory, and so on. Last year we have studied permutation, combination, induction. You can remember in permutation, combination, induction, we were learning about different values, distinct values, n. We did not see about decimals. We were only telling about whole numbers. This year, we are going to learn about operations, some logical operations I can say, certain fundamentals what are very much necessary for computer science. Operations, when I say, it can be done in only one element. For example, if I tell me negative of 7. What is negative of 7? My answer is minus 7. Suppose I ask you, what is negative of minus 7? Now my answer is plus 7. So, I ask you some operation on one element. Such a thing we call unary operation. Unary tells me single. So, finding negative of a number, I can give as an example. Suppose I ask you, what is 9 minus 7? Now, what is my answer? There are two elements involved and my answer is 2. Suppose I ask you 9 plus 7. Now also two elements are involved and my answer is unique, I will say. So whenever I am performing an operation for two elements, you call it as binary. The word bi means two. So binary operation involves two elements and mostly the answer is unique. I want to extend 3 elements, 4 elements, 5 elements and so on. When there are n elements, we say n-ary operation. So this is in general, and this year we are going to concentrate on binary operation. Binary operation, we mainly say two ideas. It exactly involves two elements and of natural numbers. Capital N stands for natural numbers. The resulting element is also a natural number. To be specific, I can also define like this. To define an operation, I must have a set first of all. What is the set? We call S, the notation, as a non-empty set. And I can say star is an operation. That star can be addition, subtraction, multiplication, or bigger of two numbers, smaller of two numbers. I can define in my own way. So star is an operation defined on S. I call star is binary if for every A, B, two elements in S, the answer for A star B is unique and A star B belongs to S. So binary operation, this idea we will use in almost all the problems of first exercise. Take two elements in S, any two elements in S. Perform the operation. My answer should be unique and it should belong to the set. Now the question is, suppose I give you addition in the set of natural numbers. Is it binary? Yes. I add two natural numbers. My answer is a natural number. But is subtraction binary in N? Of course, no. Because 9 minus 7, 2 belongs to N. But minus 9 plus 7. This is also subtraction only. 7 minus 9 I am putting. So 7 minus 9, my answer is minus 2. That does not belong to N. So subtraction is not binary in natural numbers. So 7 minus 9. 7 is a natural number. 9 is a natural number. When I perform the operation subtraction, my answer is minus 2. That does not belong to N. Therefore, subtraction is not binary in N. Like this, you can check whether a given operation is binary or not. Suppose I take multiplication 9 into 7. My answer is also a natural number. So, addition is a binary operation in N. Multiplication is binary in N. But subtraction is not binary. In the same way, division is also not a binary operation in N. Because when I divide, fractions will come. Fractions do not belong to natural number set. So, subtraction and division are not binary in N. So, depending on the set of elements that I take, I can check whether an operation is binary or not. Whenever A comma B belong to S, A star B also belong to S, I can say closure property is true. The word closure tells me the set is closed. So, two elements are there. That answer also is inside the set when I perform the operation. Such a set we say closed set, and S is said to have closure property whenever A comma B belong to S, A star B is in S. Now what is your conclusion? Whenever star is binary, it is said to be closed also. So closure property I can say is true whenever star is binary. Let us see to some of the symbols that we use in discrete mathematics. Symbols that we use. This symbol we read belongs to. Same thing if I invert and write, I call such that. And this symbol like V or upside down A, I can say for every. This symbol already you are familiar with, implies. And this symbol reverse E, I will say there exists. So in discrete mathematics, when we need to write a lot, we use symbols to reduce our wording. Exercise 12.1, question number 1. Determine whether star is a binary operation on the sets given below. The set is R. R stands for real numbers. What do you mean by real numbers? Plus numbers, minus numbers, whole numbers, fractions, decimals, square root of positive numbers. So all these things will come under R. So maybe the very big set till what we had learnt in standard 11. So this year we learned complex numbers. Remember that contains square root of negative numbers too. So R contains all the numbers that we know except root of negative numbers. Now the question is A dot mod B. A star B is A dot mod B. Let us take A comma B belong to R, any two elements. What about mod B? It is positive and so it belongs to R. A dot mod B also belongs to R. So what is binary operation definition? Whenever AB belongs to R, A star B also belongs to R. So I started with AB belong to R. I ended with A star B belongs to R. Therefore, star is binary in R. So it's a simple process. We just explain the terms. What do you mean by binary operation? Two elements. For every two elements in R, that answer should be in R. So obviously A dot mod B is in R. Whatever may be A and B value, whenever A, B belong to R, A star B belongs to R, and therefore star is binary in R. Second subdivision, A star B equals minimum of A comma B. How will you define? A comma B belong to capital A. What is A in this problem? 1, 2, 3, 4, 5. Now what does star say? Star tells find minimum of A comma B. What does this mean? My answer is A if A is less than B. My answer is B if B is less than A. In both the cases, my answer is either A or B. So A, B is already in A. Therefore, A star B belongs to A. And hence, star is binary in A. So it's a simple problem. My question is minimum of AB. For example, I take minimum of 1, 2. My answer is 1. I take minimum of 5, 2. My answer is 2. So in every case, the minimum will be either the first number or the second number, but both the numbers are in A. So my answer, A or B, is obviously in A, and therefore star is binary in A. Third subdivision, A star B is A root of B. Check whether it is binary in R. We know A comma B belong to R. But if B is negative, I say B is negative, root of B does not belong to R because root of negative number is not in R. Therefore, I will say A star B does not belong to R, because if root B does not belong, A root B also does not belong, and therefore I will say A star B does not belong to R implies star is not binary in R. Notice the condition. Every time it need not be a binary operation. Certain times the answer may not belong to the set. R is set of all real numbers, positive, negative, decimal, fraction, everything. If B is negative, we will say root of B does not belong to R. In that case, A star B also does not belong to R, and we will declare star is not binary in R. Second question, on Z, define an operation like this by m star n equals m power n plus n power m, where m and n are in Z. As I see this, m power some number, n power this number. Will the answer be in n? Whenever I want to say that you are a very good child, I need to give almost all sorts of examples to express that you are a good child. But if I want to say that you are bad, do I need to give more examples? No. One example will do. to express that you are bad. So, true when I want to say, I need to give umpty number of explanation. But false when I want to say, one example I quote, that is enough. So, to say something wrong, if I say only one example, see, it is fully a white sheet. In that sheet, it is white, I will say. But if I keep one black dot, immediately you will say it is not white. Everybody will look at the black dot only. So, false when I want to prove. One example is sufficient to say it is false. Now here, how am I going to say it is false? Say 2 power 3 plus 3 power 2. If it is of this pattern, belongs to Z. Suppose it is 2 power minus 3 and minus 3 power 2. Does it belong to Z? No. Because 2 power minus 3 will become 1 by 2 power 3. The answer is 1 by 8. 1 by 8 does not belong to Z. Then what is Z? Z is a set of integers. Only the plus and minus numbers with 0. Fractions do not come in Z. So, when the power is negative, my answer does not belong to Z. So, star or the operation that is given here is not binary in Z. Now, let us put it in proper words. When the power n is equal to minus p, where p is a positive number, m power n plus n power m will become m power minus p plus minus p power m. This becomes 1 by m power p plus minus p power m, which does not belong to Z, because fractions are not in Z. Therefore, the operation that they give is not binary. So, we will say the given operation is not binary in Z. A simple problem, but we need to put it in proper words when we explain. So, what is the reason for it not to be binary? Whenever the power is negative. So, treat n, one number, as negative of p, where p is a positive number. Minus p tells me it is negative. So, when the power is negative, I write 1 by m power p, which becomes a fraction. Fraction is not in Z, and therefore it is not binary in Z. M, n belong to Z does not imply m, that operation given n, belongs to Z. So, whenever mn belongs to Z, implies I will say it is binary. Now, I will say does not imply that operation belongs to Z. So, we are giving an example to quote that it is wrong. Question number 3. Star is a operation defined in real numbers R by A star B equals A plus B plus AB minus 7. Is star binary in R? If so, find 3 star minus 7 by 15. Let us say for every A, B belong to R. The problem in R is only square root of negative number does not belong to R. All other numbers, see, A, B, AB minus 7, all belong to R. Implies A plus B plus AB minus 7 also belongs to R. Implies A star B belongs to R. Therefore, I will declare star is binary in R. So, whenever A and B are real numbers, adding A and B or adding the product or subtracting 7, the entire answer is a real number. Therefore, star is binary in R. we need to calculate 3 star minus 7 by 15. What is my answer? Wherever A comes, put 3. Wherever B comes, put minus 7 by 15. So what is the operation? A is 3, B is minus 7 by 15 plus A is 3, B is minus 7 by 15 minus 7. Simplify the answer. 3 minus 7 by 15 plus into minus minus we can cancel. It is 7 by 5 minus 7. Taking LCM, that is 15. 45 minus 7 minus 21 minus 105. We get minus 88 by 15. So third problem, we are checking whether star is binary. We have said yes. If so, wherever A comes, put 3. Wherever B comes, put minus 7 by 15. Simplify and get minus 88 by 15. Question number 4. Let capital A is set of all numbers of the form A plus root 5 into B, where A and B are integers. Check whether usual multiplication is a binary operation on A. Given a format like this, try to write two elements of A. How the elements of A will look alike? A plus root 5 into B. Same way tell another number C plus root 5 into D. Like this you can say anything. E plus root 5 into F. Y plus root 5 into Z. So like that. One is free from anything. Another one is multiplied with root 5. So I have taken two elements in A, where A, B, C, D are all integers. That is the idea. When I write the format, A, B, C, D are all from integers. Now my question is multiplication. How will you multiply? Ordinary multiplication. A plus root 5B into C plus root 5D. A into C, A into root 5D. Root 5B into C, root 5B into root 5D. If I multiply, my answer AC, A root 5D plus root 5BC plus root 5B into root 5D, or AC plus root 5AD plus root 5BC plus root 5 into root 5, 5BD. Connect terms without root 5 and terms with root 5. So AC plus 5BD into root 5 into AD plus BC. I have something without root 5 and something with root 5, same format. So it belongs to A. Therefore, usual multiplication is a binary operation on A.